Greetings and welcome to my YouTube channel and welcome to my course on calculus. This course will be a first course in calculus and is suitable for anybody who's studied pre-calculus, trigonometry, geometry, and algebra. Okay, so shall we begin? So calculus is often called the study of change. And we can consider calculus to be in several different branches. Well, at least two. We could describe calculus as something called differential calculus. And we could describe calculus as something called integral calculus. But there are also topics within calculus that aren't necessarily in these two sections, such as series and sequences, which I will cover. And also, we will discuss parametric equations, which will actually be in. So the parametric equations are able to apply differential. We're able to apply the concepts of differential and integral calculus onto parametric equations. So that will be similar ideas and theorems, but different ways of calculating them because of the nature of the equations. And then there's also a such thing as stochastic calculus, which is useful in financial applications. So in this course, we will cover single variable calculus, firstly differential calculus, and then secondly integral calculus. And then from there, we'll actually, this is going to be in this order. This one will go here, and then we'll go on to series and sequences after that. Okay, so essentially, if you were to look at the AP calculus syllabus or the syllabus at a first year university or a first calculus course in a university, those are the topics I'll be covering. So to start, I want to motivate the idea of differential calculus. And I'll start by talking about linear functions, aka these are lines. And we know a line to be of the form f of x equals mx plus b. Typically, we know this where m is our delta y divided by delta x, our gradient in some places, or slope in other places, which is simply the change in y divided by the change in x if we're given two pairs of points, x1, y1. So for x1, y1, and x2 and y2. And we'll go ahead and say where our domain is the real numbers. Okay, so we're going to be using real numbers. All right. So a linear function, the important thing about this linear function, well, there's two things. And actually this function is, it seems so simple when you learn it at first, but actually this function is the basis for most of quantitative methods and trying to establish some sort of prediction model between two variables that possibly have a linear relationship. So, and although in this case, what we have here, this is a function that has a functional relationship where it meets the definition of a function. But when you get into quantitative methods or data science, we have two variables that have a statistical relationship that we try to describe with this idea of what's called the general linear model. And it's based on this idea of having a linear function where you have this gradient here, which is describing what? It's describing the rate of change of the function. And then here we have our intercept. And so this will always be the coordinate 0, b. Okay, so then if we want to graph a line, we can graph a line on the xy coordinate plane. And using the equation, we can always graph this line. So here's x and here's y. And if I want to graph this line, goes mx plus b, then what will it look like? Well, I'll have this one point here, certainly, which would be when x is 0, y is b. And then we could say I'll have some other points on my line here. So let's just make a different color point. So here I'll have the first set of points, and here's my second set of points. So here I've got x1, y1, and then here I've got x2, y2. And so then we can define our gradient to be like this. Well, I want that to be a different color. Wait. So, all right. So let me just explain this. Okay, there we go. And so what is the gradient here? The gradient is the change in the gradient, or the slope, if you like. So if I say gradient, let me make a note of that. So just a little terminology, because there's different terminology all over the world. So gradient is equivalent to slope. These mean the same thing. And what do they mean? Well, here I've got some point x1, and then here I've got some point x2. Not a point, rather, but well, I guess I'll call it a point. Here I've got my y1, and here I've got y2. So then the difference between x2 and x1, we just use the typical notion of distance where we subtract one from the other. So then this distance here is x2 minus x1. That becomes my delta x. And so this little dashed red line is the difference from one x coordinate to the previous, or if you like, you can go the other direction, doesn't matter, because we'll be talking about a distance and it has to be positive. And then delta y is going to be here. So the distance between y2 and y1. Okay, so that is our m, and here is our b. So m is delta y divided by delta x. Now, one of the unique features of a line is that this gradient that we're talking about, which tells me the ratio of the change from one point to the next, if you like, the ratio of the change in y over the change in x, it will remain constant for the entire domain of the function. So the linear function has the unique feature of having a constant slope. So we can say that linear functions have a, oops, let me write that. They have a constant slope, which in other words means they have a constant rate of change. So no matter which 2 points I choose on the line, I will always find the same rate of change. Okay. Now, the type of slope, the type of gradient determines the type of a line. Okay, so let me go into this. So we have, basically we have 4 types of lines. And the lines are based on the gradient. So if the gradient is greater than 0, well, let me make some preamble here. So let me say it like this. So for any f of x equals mx plus b, where we've got our points xi and yi are real numbers, we have, so first of all, we have if m is greater than 0, then our function f of x is increasing. Well, I should say our line more specifically. 2, if the slope is less than 0, then f of x is decreasing. And did I say 4 types of lines? Yeah, okay, I did, and I'm correct. Okay. If m equals 0, so if our slope is 0, then that means that there's no change, right? There's no change from point to point. So over any particular interval, we're not increasing, we're not decreasing. And since we have linear functions where if it's increasing in one place, it's increasing everywhere because the rate of change is constant. If we have that the slope is 0, then that means that f of x is horizontal. That means that it's a flat line. All right, and then we have one more. And we don't really have the language at this point to adequately describe this. But I can say if m equals delta y over delta x, and I'll say it like this, and we'll say that delta x is getting closer to 0. So if we have this and delta x is getting closer to 0, then m is getting closer to infinity. So in other words, m isn't getting closer to infinity. That's sort of a weird thing to say, right? Because you can never get closer to infinity. So what we mean is that the slope is getting larger without any maximum value. So if that's the case, then we say that the slope is undefined. In other words, I think I just thought of a better way to say this. So let me say it like this. So this will certainly be true. So if this is our slope and delta x is going to 0, then m goes to infinity. Then we say our slope is undefined, which is exactly happens, precisely when x1 equals x2 equals xn for all x in the domain of the function. So, all right, so what does it mean? It means that this line will have the same x value for every y value. And what does that look like? So that means then f of x is vertical. So it means we have a vertical line, and the slope of a vertical line, we typically say it's undefined. All right, so let's take a look at what these all look like. So we need, we'll need some XY coordinate planes first. Okay, and let's use this one, say is yellow. This one will say is blue. This one will say is green. And let's make this one here, since it's already like, well, it's not quite. I wonder if I can move that. Can I move it? No. I've got an idea. Okay, and there's my vertical line. Okay, so let me just label everything here. And if you're watching this and taking notes, probably a good idea to label it. So this one is where the slope is positive, it's greater than 0. This one, my slope is negative, so it's decreasing, right? And this one, we have a horizontal line, which means that the rate of change is 0. It's not changing at all, so m equals 0. And this one over here, we've got the case where we've got a line where the slope is basically something over 0, so it's undefined because we have the same x value, right? And you think about the same x value for every y value. So what's the definition of the gradient? It's the change in y over the change in x. So it means that every x value is the same, so I'll always have 0 in the denominator. And so we say this slope is undefined. And some people write it like it's equal to infinity, but that's impossible. So we'll say m is undefined. And I do want to mention one other thing here, and that is these two have your typical formula. F of x equals mx plus b, where of course the m is positive. This one is f of x equals mx plus b, and it's negative. But these two have a different type of formula. This one has the same y value for every x. And so if we call this number k here, this is y equals k. And so that would be the equation for horizontal line. And likewise here, if I call this one h, if this x value equals h, then that's the equation of this line, x equals h. Okay, so if you have a vertical line, it will always be x equals something and no y value, because it will take on every y value. And if you have a horizontal line, it will always be y equals k. Okay, so why are we so interested in lines? Because lines are, believe it or not, lines are really important to calculus. And so we start with the idea of a line, and we look at how we can examine the rate of change by using the gradient. One other thing I want to mention about before I switch into the serious motivation is as the idea of steepness. Or the decreasing rate. So, or I could just call this the rate of change. So if I draw this little plane here, then we can talk about steepness in terms of the size of the gradient. So that's one way to talk about steepness, right? So if I draw this line here, actually I wanted a straighter line than that. if I draw this line here, there we go. Let's put it like, let's make it like this. Okay, so here's my first line. And we'll call it g of x. And then I draw a second line like this. Then we can start to talk about which line is increasing faster or which line is steeper than the other line. And you can get an idea about steepness basically by looking at, let me change this color. If I were to draw this line here, and then draw a line maybe like here, and now I compared the angle between the line I've just drawn, and basically I'm saying, like, if I compare the angle between the line and the x-axis. Okay, so this one, g of x, doesn't cross the x-axis. But let's say I move the x-axis up to where it's crossing. Then what I want to do is look at this angle here. Oops. I'll look at this angle, call it theta 1. And if I look at this angle here, so this one is crossing here, so I can look at this angle here. I'll call it alpha 1. So if the angle is larger, that means the line is steeper, right? But another way that we could look at this would be to look at, so if I look at the gradient for f, it will definitely be larger than the gradient for g. Okay, so that's just an idea about steepness. So in other words, this line is increasing faster than this one. Okay, and if I draw a flat line, well, then it's not changing at all. There is no increase or decrease on a horizontal line. And so in this case, the m is 0. Okay, and so that's where you get the idea of steepness, and you know, how one line could be increasing faster than the other. It depends on if the slope is larger or not. And it ties back into this angle that we're making with the x-axis. Okay. All right. So now let's talk about, when do we start when does the calculus start, or what's the motivation for calculus? Well, there's a story about Isaac Newton was studying, I think maybe he was studying some of the astronomical records that were kept by Kepler. And Kepler was an astronomer, and he was in cahoots with another astronomer named Tycho Brahe. He was a very interesting guy, a very wealthy astronomer who had a lot of equipment. And Kepler was sort of from a less aristocratic background, I suppose. And so they worked together, and Kepler got all these observations about orbits of planets, and they wanted to study these. And I could have it wrong. I don't know the timelines, but if it's wrong, you can check it and fact check me, because I'm trying to think about back to my astronomy class. But I think maybe, I don't know if the timeline's right. But anyways, the basic idea was that Newton was wanting to study the rates of planets that are moving in orbits around the sun. Right, is that right? Yep. So the problem was that the planets are orbiting in an elliptical orbit. So it's not quite a circle, we call it a deformed circle. And so how can you calculate the rate of change if it's not moving in a straight line, where we have formulas and so forth to describe the rate of change? Well, they had to invent calculus to be able to study the rate of change for a function, or in this case, it was an ellipse that's describing a motion that's nonlinear. And so that's the first idea in one of the first ideas that we want to try to solve is called the tangent problem. And so the idea is this: we've got some function here, and we'd like to know what is the rate of change of this function at any given point. But the problem is that the function is nonlinear. And so if I try to, for example, let's just say I choose this point here. If I want to find the rate of change at this point, well, how can I do it? Because first of all, I only have one point. And if I look over here to try to use the gradient formula that we've seen before, what's going to happen is that I'm not going to have the same rate of change. So the idea of steepness, right? You can see that down here. Let me just grab this thing. Yeah. So you can see, like, over here, this part of the graph is not as steep as over here. So in other words, the rate of change for the nonlinear function is not constant. And so how can we describe the rate of change if we don't have a mechanism by which we can do that? So Newton had to invent calculus, and simultaneously, I think Gottfried Leibniz also did so, and there's some credit to a mathematician or computer scientist named Sophia Lovelace. Okay, so, but a lot of people, wasn't it Newton who said, if you can see far, it's because you're standing on the shoulders of giants? So it's a collaborative effort of many people, but some of the initial people get the credit, and they become part of the folklore, right? Well, I guess it's not folklore, but the the history. Yeah, I guess to me it's folklore because I don't have the dates and everything memorized. Yeah, and I've just learned it through sitting in classes. Okay, so the rate of change of this nonlinear function is not constant, and aside from that, also maybe I'm not interested in every single point. I'm only interested in, like, sorry about this mouse clicking, but I'm going to make this easy. There we go. Maybe I'm only interested in one place. Like, let's say I'm interested in this point here. So let's see. So let's say I'm interested in just this point. Well, one thing that we can do with the gradient function is we can imagine that we've got some, I'm going to change this to I'll do that later. So even though our function is nonlinear, what we can do is we can still use our gradient formula, but it's not going to give us the slope of the function at one specific point. Instead, what it's going to do is it's going to give us the average by giving us the slope of this line that's passing through 2 points. So this red line that I've just drawn here, this is called a secant line, which comes from the Latin word to cut. And so it cuts through the function in 2 points. And so we can use the gradient to find the slope of this line. And it turns out that this line will be the average of the rate of change for our nonlinear function, which I'm going to call f, on this interval from x1 to x2. So if I take f of x1, oops, let me undo that. If I take f of x, we'll do f of x2 minus f of x1, divided by x2 minus x1, then what will happen here is that I'm going to get, hold on a second. Here, I'm going to get the average rate of change of the function on this interval. All right, so it cannot give me the instant rate of change because the rate of change is not constant. But I can get the average rate of change. And so here I can say that the slope of the secant line, so the secant line is that passes through these 2 points through, so I've got x1, y1, x2, y2 is the average rate of change of f of x, our nonlinear function on this interval, on the interval from x1 to x2. Okay, so I can get an average rate of change, but perhaps we want to be more precise. And if that's the case, then we will need to figure out a way to be more precise. And it turns out that one way we can do that is by basically moving the points closer together. Okay, so just a moment here. So that's what we'll do. And let me just kind of like scroll up, and I'm going to make a new graph now. And so I'm just going to draw what actually happens here. And we'll go like this. So I've got y here, and I've got x, and then I've got my nonlinear function. Let's call it some parabola. Okay. So this is just some parabola called g of x. And then I've got some points of interest here. So this is my point of interest that I would like to know the rate of change at. And this is my other point over here. So as we mentioned before, we can definitely connect these 2 points to get the average rate of change by finding the slope of the secant line. But what's even more interesting is that I can actually move the line closer to the graph by making a new line where the points are getting closer together. So let me label this down here. So I'm going to say, let's just call this point A. And we'll call this point out here, it's just going to be X. So this will become not f of A, but g of A, since I called it, well, let me call it f of A. Call it f of x, that's the classical thing to do. And so this is g of A, and then this guy over here will be g of x. Okay, and so what happens is we're going to move this closer and closer. So I'm going to move it here, and then draw a line, draw a new line. And that's going to give me even better approximation. And I'm going to continue this idea until eventually I've got a line here that looks like this, where now this line is not cutting through the curve. Now this line is only touching the curve in one point. And hold on, let me back up. So now I'm touching the curve in one point here. And at this particular point, if you were to take this little blue box that I've drawn here, Okay, let's do like this. If you take this blue box that I've drawn and you magnify it like this. So let's magnify the blue box. And then you magnify the, magnify the nonlinear function and the secant line. What we will see is that they are coinciding at that point. So that there's no difference between the function at A and the tangent line at A. Okay, so this is the point A, f of A, right? Why did I write G again? I don't know. Sorry, I changed it to A, but then I forgot to change that one. A and f of x. So if we move the secant lines closer and closer and closer until we have this tangent line, now if I take the slope of this tangent line, then I will get precisely the gradient of this nonlinear function exactly at this point, because they are coincidental, they're right on top of each other. So this will be this is the idea. Now, how do I do that? Well, we start with the gradient formula, right? So we have delta y over delta x. Okay, and then we've got, in this case, we've got f of x minus f of a divided by x minus a. And so what happens is we use something called the limit. We move this point closer and closer until we get to a point that's infinitely close to A. Okay, so this, like you've seen, I've just drawn, first I have the red secant line, and then I got a better approximation. So the red secant line definitely gave me an average, but also the average gave me an approximation for the instantaneous rate of change, for the rate of change at this one point of this nonlinear function. Then I moved it again, I got this blue secant line that got me a better approximation, moved it again, got this green secant line, got me a better approximation, and I keep moving this point until it's almost exactly A. And what that means is that we do something called the limit. We say we will take the limit as x goes to A. Now we can't let x ever equal A, because then we'll get 0. But we can get infinitely close to A. All right. And then what'll happen is we've got this expression here, minus f of A, which is giving me the slope of that tangent line. Okay, so this expression gives me the slope of the tangent line, and the tangent line is, in fact, so let me get a different color. So this expression, wait. So this is slope of the tangent line. Hold on, let me go back a couple of steps here. There we go. Okay, so this is the slope of the tangent line, which is also the gradient of this nonlinear function at that point. So it's also the slope of f of x, which is also, we'll call it the rate of change. But we can, so if we say rate of change, we can say slope, we can say gradient, all interchangeable, which is also the rate of change of our function f of x at A, at that point where x is equal to A. So at this point right here. So by using this operation, which we'll describe in great detail in the coming lessons, it lets this x value get infinitely close to this a without ever becoming a. And what that does is it allows us to create this tangent line whose slope we can find and whose slope is equal to the rate of change of the function at that point. Okay, and so now we have calculus. And the two things that we need to take away from, well, three things really. The first one is the average rate of change. So make sure you have this formula. So the average rate of change formula is, of course, it's going to be delta y over delta x, which is going to be, I'm going to use this type of notation now, f of b minus f of a over b minus a. So the average rate of change, and let me just make a little for f of x on a b. Okay, so there's the first formula we need. And then the second formula, actually, one more thing I want to write here, which I almost forgot. So the average rate of change, this is the slope of the secant line. So it's the slope of the secant line between these 2 points. Slope of the secant line passing through f of, hold on a second, that's backwards. Passing through these 2 points, we've got a f of a and b f of b. Okay, that's the first one. And the second one is going to be, we're going to call this instantaneous rate of change, because we're talking about at one precise point. Now, we said that for a linear function, the instantaneous rate of change should be the same as the gradient, right? So the instantaneous rate of change should be the same everywhere for a line. But the problem with this, and we'll look at this, how to prove it later. So let me just take a little, I'm going to stop writing this for a moment, just go off on a little tangent here about this. If I try to use this gradient formula on one point, so here's my point, right? Okay, so x1. If I try formula here, then it will fail, and you'll see why, because we're going to get y1 minus y1 over x1 minus x1, which equals 0 over 0. But we know that it has to be m, right? Because it's a line. So we'll see that we can actually prove this using the limit and using calculus. So like right now, it's hard to do it, right, without calculus. But all right, so then instantaneous rate of change, we'll be able to use this formula, equals the limit as delta x goes to 0. Actually, what did I do this time? I didn't want to do this one yet, or do I? No, I can do it now, I guess. The limit as delta x goes to 0, where we have delta y over delta x, which is equal to the limit. So I'm just going to give you, there's so many different notations as x goes to a. So remember, the change in x, delta x, was the difference between x and a. So the limit as x goes to a of f of x minus f of a divided by x minus a. All right, and that's going to be my instantaneous rate of change, i.e. this is the slope of the tangent line to f of x at a. Now, there is only one unique line that we can get the slope. There's only one unique tangent line that passes in this particular point. for this particular function. And that's a proof you can do, but we won't do it now. So the slope of the tangent line is the instantaneous rate of change for that function. So let's see, anything else? I think. So we'll talk more about this in the next lecture. But first, in the next lecture, we will look at this idea more closely, because it's sort of like, oh, by the way, here's a new tool we can use to use this. And this is what I think Newton did, was they used this limit operation. So in the next lesson, we will discuss something called the limit. And this is the limit operation. And in my opinion, the limit operation is probably the most, it's the, what is that? What is that word? It's the, something about a stone that goes in the middle of something. I don't know. It's like the most important thing. Because without this limit operation, you can't take derivatives, you can't integrate. And the reason why it works is even more interesting, which we won't really get into why the limit operation works. We will look at some, we'll look at the typical calculus definition of the limit, but we'll also look at what is called the epsilon delta definition of the limit. And so this limit operation, you should know it, learn it well, and learn its properties well, because since the derivative is a limit, and since the integrals, definite integrals, are limits, that means that they have the same properties as limits. So this whole idea of limits is going to take us a long ways, and they're really interesting. And this will be the topic of the next lecture. Okay, well, I hope this helps. If you have any comments or suggestions, please let me know. If you notice any mistakes, also please let me know.